In this lesson, we want to talk about solving trigonometric equations with multiple angles. All right, let's take a look at the first problem. So here we have the cosine of 2 beta is equal to negative 10 cosine squared beta plus 8. Now we just want to solve this from 0 to 2 pi, where 0 is included and 2 pi is excluded. Now when you look at this, if I'm trying to get cosine of beta equals some number, here you have cosine of 2 beta. Here you have cosine squared beta. So this one right here is going to be the immediate problem for us because you want to write this in terms of the cosine of beta, again, equals some number in the end. So what you would want to do is use a little identity to plug in for this guy. And coming down here, this is the one I'm going to work with. If you have cosine of 2 theta or 2 beta, whatever you're working with, you have 3 different formulas you can choose from. I'm going to work with this one. So what I'm going to do is say the cosine of 2 beta is equal to 2 cosine squared beta minus 1. So I'm just matching this formula here. I'm just taking the beta in the place of theta. And basically now you have cosine of 2 beta and cosine of 2 beta. So those match. And what you can do is take this guy right here and you could just plug it in for this guy right here. And that's going to give me cosine squared beta over here and cosine squared beta over here. So that's what I want. So let's write this as 2 cosine squared beta minus 1. Again, just taking this and plugging it in for this. So that's how I get this left side now. So this equals, on the right, nothing's going to change. So this is just negative 10 cosine squared beta and then plus 8. Okay, at this point, I want to get cosine of beta equals some number. If you have a squared guy involved, then you should be thinking about factoring, or in some cases, the quadratic formula. But for this particular problem, you could actually solve it using the square root property, and it's going to be a lot faster. You could solve this with factoring if you want to, but it's going to take a little bit more time. So what I'm going to do is isolate cosine squared beta on one side and then have a number on the other side so I can use the square root property. So I'm going to add 10 cosine squared beta to both sides of the equation, just like that. And so right here, this is going to cancel. And then the other thing I'm going to do is add 1 to both sides of the equation. So this is going to cancel. So on the left, you have 2 cosine squared beta, then plus 10 cosine squared beta. That is 12 cosine squared beta, and this equals 8 plus 1 is going to be 9. Now, what you would want to do, since 12 is multiplying the cosine squared beta there, you would divide both sides of the equation by 12. So you want cosine squared beta by itself to use the square root property. Okay, so this right here is going to cancel, and you get cosine squared beta is equal to, for 9 over 12, again, each is divisible by 3. So 9 divided by 3 is going to be 3, and 12 divided by 3 is going to be 4. So this is cosine squared beta is equal to 3/4. And now we can use our square root property. Again, if we have something like, let's say, x squared equals 3/4, then by the square root property, we can say x is equal to plus or minus the square root of 3/4. So that's the square root of 3 over the square root of 4, which is 2. So x would be equal to plus or minus the square root of 3 over 2. Well, here it's the same thing. I'm just going to get that cosine of beta is equal to plus or minus the square root of 3/4. And again, this becomes the square root here of 3 over the square root of 4. And the square root of 3 really can't do anything with that, but the square root of 4 is going to be 2. So the cosine of beta is equal to plus or minus the square root of 3 over 2. Okay, let's come to the unit circle, and let's actually write this as the cosine of beta is equal to the square root of 3 over 2, and then I'm going to write or the cosine of beta is equal to the negative of the square root of 3 over 2. So for beta here, we're going to look in quadrants 1 and 4, where cosine is positive, and I'm looking for an x-coordinate of square root of 3 over 2. So right here at pi over 6, and then coming down here, it's going to be at 11 pi over 6. So notice it's pi over 6 here, and then a pi over 6 reference angle here at 11 pi over 6. Then if I'm looking for cosine of beta to be equal to negative square root of 3 over 2, well, I'm looking in quadrants 2 and 3, where cosine is negative. So you can just think about a pi over 6 reference angle, or again, you could just look for that x-coordinate of negative square root of 3 over 2. So that's going to be right here at 5 pi over 6, again, pi over 6 reference angle, and then right here at 7 pi over 6, again, pi over 6 reference angle. So because we're working in the interval, where beta is greater than or equal to 0 and less than 2 pi, we can just list these 4 solutions and be done with it. So we're going to say that beta is equal to, we have pi over 6, we have 5 pi over 6, and then we have 7 pi over 6, and then lastly, we have 11 pi over 6. All right, let's take a look at the next problem. So here we have 4 sine of beta cosine of beta equals the square root of 3. We want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So the first thing is, when you look at this equation, it might not be immediately obvious what you can do, but if we look at our identities, again, you have something like this double angle identity, the sine of 2 theta equals 2 sine of theta cosine of theta, which you can use to solve this equation. So I'm going to write this as the sine of 2 beta is equal to 2 sine of beta cosine of beta. Come back up here and paste this in. Now, this might not be immediately obvious, but we're going to take this right here and match it with this right here. Now, right now you have this 4 right here and you have this 2 right here. So you've got to rewrite this to where it's going to match. So this is just straight multiplication. So for 4, I could really write that as 2 times 2. So I could say that this is 2 times, and then it would be 2 sine of beta cosine of beta, and this equals the square root of 3. So this 2 times 2 sine of beta cosine of beta gets me back to 4 sine of beta cosine of beta. So I haven't done anything illegal. If you look at this guy right here, now it matches this guy right here perfectly. 2 sine of beta cosine of beta, 2 sine of beta cosine of beta. So that means I can legally take this right here and I can plug it in for this right here. So what that's going to do for me is I'm going to have 2 sine of 2 beta equals the square root of 3. So I'll be able to get it to sine of 2 beta equals some number, and I'll be able to get a solution. So let's go down and make a little substitution here. So I'm going to have my 2, don't forget about that. And then what is it multiplying? Again, for this, I'm plugging in this. So I'm going to have my sine of 2 beta, and this equals my square root of 3. All right, so just like I said, we want to get sine of 2 beta equals some number. Right now you have 2 that's multiplying the sine of 2 beta. So let's divide both sides of the equation by 2. So this is going to cancel, and we're going to get the sine of 2 beta is equal to the square root of 3 over 2. All right, there are quite a few ways you could solve this. What I'm going to do is stick to the method that the book uses because we're solving over a specific interval. We're not giving the general solution. So I'm going to start with the interval we were given. So we have beta is greater than or equal to 0 and less than 2 pi. Well, right now I have 2 beta. So I'm going to multiply each part of this inequality here by 2. So 0 times 2 is still 0, and this is less than or equal to. Beta times 2 is 2 beta. So now this matches this, and then this is less than 2 pi times 2 is 4 pi. So right now I'm going to work in this interval because, again, I have the sine of 2 beta, not the sine of beta. So that's why I'm adjusting this interval. So let me move this up here, and we're going to think about where are the sine values square root of 3 over 2 in this interval right here. So let's start with the standard interval. So just going from 0 to 2 pi, 0 included, 2 pi excluded, and that's going to give you a pi over 3 solution. So there's your square root of 3 over 2 for the y value, and then here's your square root of 3 over 2 for the y value as well. So that's at 2 pi over 3. But again, to get all of the solutions in this interval, what you have to do is take those solutions and you have to add 2 pi to them in order to get all the solutions in this interval. So I'm going to take and list pi over 3, and then let me list 2 pi over 3. And then what I would have to do is, again, take pi over 3, so pi over 3, and I've got to swing around by another 2 pi. So let me go plus 2 pi, so that's 6 pi over 3 if I get a common denominator. Let me make that 3 a little bit better. So that's 7 pi over 3. So let's put that up there. So that's 7 pi over 3. So again, starting here, just swinging around by another 2 pi. You've got to do the same thing here. So you're going to swing around by another 2 pi. So let's put this as 2 pi over 3 plus, again, 6 pi over 3. So 6 pi over 3 is, again, 2 pi written with a common denominator. So this would be 8 pi over 3. So 8 pi over 3. So that's basically all you have to do for this part. The only thing is, you have not solved for beta. You've solved for 2 beta. So in other words, you could say that 2 beta is equal to this right here. Let me just drag this down. And I don't know if that's going to fit. And let me just grab this real quick and paste this in and go to another page. So basically, if you want to solve for beta, you would divide everything by 2, or you could multiply everything by a half. So in other words, you could say that beta is equal to, you'd have pi over 3 times 1/2. So that would be pi over 6. So pi over 6. And then you'd have 2 pi over 3 times 1/2. So the 2's would cancel there. So that would be pi over 3. So pi over 3. And then you'd have 7 pi over 3 times 1/2. That would give you 7 pi over 6. And then lastly, you'd have 8 pi over 3 times 1/2. So here, 8 divided by 2 would give you 4. So this would end up being 4 pi. So 4 pi over 3. So these are your solutions in terms of beta. So if you plug those back into the original equation, they will work, and they are in our interval where beta is greater than or equal to 0 and less than 2 pi. So beta is pi over 6, pi over 3, 7 pi over 6, and then 4 pi over 3. All right, let's take a look at another problem. So we have negative 9/2 is equal to negative 4 plus the cosine of beta plus 7 pi over 4. We're solving this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So I'm going to get cosine of beta plus 7 pi over 4 by itself. So that'll be on one side. There'll be a single number on the other side. So that's the first goal. So let me write this as negative 4 plus cosine of beta plus 7 pi over 4. And then this would be equal to, you have this negative 9/2. Now, if I want cosine of beta plus 7 pi over 4 on one side by itself, I've got to get rid of this negative 4 here that I'm adding to this. So I'm going to just add 4 to both sides of the equation. This will cancel. And on the left, I have what I want. So this is the cosine of this beta plus 7 pi over 4. And this equals, over here I would get a common denominator. So let's write 4 as 8 over 2. I'm just going to multiply by 2 over 2 to do that. So again, this would be 8 over 2. So 8 over 2. And negative 9 plus 8, that's negative 1. So this would be over the common denominator of 2. So this is equal to negative 1/2. Now this is the part where people tend to get confused. Essentially what you're going to do is adjust your interval. You don't have beta. So if you were solving cosine of beta equals negative 1/2, well then I could go through and I could say, well, where's the x coordinate negative 1/2? We're going to have right here at 2 pi over 3. And then you come over here, and that's going to be at 4 pi over 3. We don't have that, though. We have this beta plus 7 pi over 4. We don't have beta. Well, I can adjust that interval. We had beta is greater than or equal to 0 and less than 2 pi. Well, instead of beta, I have beta plus 7 pi over 4. Okay, well, I'm just going to add 7 pi over 4 to each part. So 0 plus 7 pi over 4 is 7 pi over 4. This is less than or equal to beta plus 7 pi over 4 is beta plus 7 pi over 4. So this matches this, and this is less than 2 pi plus 7 pi over 4. So if we do 7 pi over 4 plus, let's go 8 pi over 4, just writing 2 pi with a common denominator, this would be 15 pi, so 15 pi over 4. So 15 pi over 4. So if we had cosine of beta equals negative 1/2, again, I would have this 2 pi over 3 and this 4 pi over 3. But in this case, we have the cosine of beta plus 7 pi over 4. So when I adjust this interval to this one right here, let me get rid of this one right here so this is crystal clear. What I'm going to do is look for where the cosine value is negative 1/2 in this interval. So you would start at 7 pi over 4. So in other words, you've already swung around by 7 pi over 4, and then you want to swing around by another 2 pi to end up at 15 pi over 4, even though that's not included. So you're going to catch this guy right here and this guy right here again, but it's not going to be 2 pi over 3 or 4 pi over 3. It's going to be you adding 2 pi to those angles. So what you would do is you would say that beta plus 7 pi over 4 would be equal to, you're going to take this 2 pi over 3, so 2 pi over 3, but now you've got to add 2 pi to that. So that's going to be me adding 6 pi over 3. So that would give me 8 pi over 3. So you can get rid of these middle steps here and just say this is equal to 8 pi over 3. We'll solve this for beta in a moment. Let's just do the other one. So then again, you have this beta plus 7 pi over 4 is equal to, again, you're going to take this 4 pi over 3. So this 4 pi over 3, and then you're going to add 2 pi. So you're going to say this is plus 6 pi over 3. So this gives you 10 pi over 3. Let me move this down here so this is more clear. Now, I know the first time you do this, this is super confusing, but just think about the fact that, again, you started here at 7 pi over 4. That's where the interval is beginning. So if I'm starting here, by the time I swing around, this is not 2 pi over 3. This is 2 pi over 3 plus 2 pi. So that gives me that 8 pi over 3. And then as I continue, this is not 4 pi over 3. This is going to be 4 pi over 3 plus 2 pi. So that's that 10 pi over 3. So you've got to adjust things because we're not solving cosine of beta equals negative 1/2. We are solving cosine of beta plus 7 pi over 4 equals negative 1/2. So everything got adjusted. So let's go ahead and grab this. And I'm just going to come down here and we can solve these pretty easily. So let's go OR there. I'm going to subtract 7 pi over 4 away from each side of the equation over here. So this is going to cancel. You're going to have beta is equal to 8 pi over 3 and then minus 7 pi over 4. You need a common denominator, so let's multiply by 4 over 4. Let's multiply this by 3 over 3. So this would be 32 pi over 12. So 32 pi over 12, 21 pi. So 21 pi over 12. So this would give me 11 pi, so 11 pi over 12. So that's one solution. Let me get rid of this and just write this as beta is equal to 11 pi over 12. And let me solve this one now. So I'm going to subtract 7 pi over 4 away from each side of the equation. So that cancels. You get beta is equal to, let's go 10 pi over 3. I'm going to just multiply this by 4 over 4 now to get a common denominator, and then minus 7 pi over 4 times 3 over 3. So we will say that beta is equal to 10 pi times 4 is going to be 40 pi, and this is over 12, and then minus 7 pi times 3 is 21 pi. So 21 pi, and this is over 4 times 3 is 12. So 40 pi minus 21 pi is 19 pi. So this is 19 pi over 12. Let me just put a comma here and put 19 pi over 12. So those are your solutions in that given interval, again, where beta is greater than or equal to 0 and less than 2 pi. Okay, let's take a look at another problem. So here we have the cosine of 6x is equal to negative sine of 4x plus the cosine of 2x. So here we're going to solve over this interval from 0 to pi, where 0 is included and pi is excluded. When you solve a problem like this that involves these sum to product identities, in most cases, you're not going to solve that over an interval because there's just too many solutions. You will give the general solution. Let me start this problem off as saying we have the cosine of 6x. I'm going to add the sine of 4x to both sides, and I'm going to subtract the cosine of 2x away from each side. So let me subtract away the cosine of 2x first. So I have this. And then I'm going to add sine of 4x. And then we're going to say this equals 0. Okay, let's grab this real quick. And let's come down here. So I have our little identities set up for us. So these are the, again, sum to product identities. So we have this cosine of A minus cosine of B. Here you have cosine of 6x. So 6x is your A minus cosine of 2x. So 2x is your B. Let me actually slide this down. And I'll write this out first, and then we'll plug in. So if you had the cosine of 6x minus the cosine of 2x, so I'm just going to do this part right here. This is equal to negative 2, and then sine of, you have a plus b over 2. So this plus this. So 6x plus 2x over 2. And then you have your sine of a minus b over 2. So 6x minus 2x. So 6x minus 2x, again, this is over 2. 6x plus 2x is 8x. So this right here would be 8x over 2. So this 8 would cancel with this 2 and give me a 4. So this would be 4x right here. So let's write that like that. I'm just going to wrap this for clarity. And then here, 6x minus 2x is 4x. And so this would be 4x over 2, which is 2x. So let's write the sine of 2x. Now, since this right here matches this right here, we can take this guy right here and plug it in for this right here. Now, why are we doing that? Notice you'd have a sine, and then you have a sine. And more specifically, you have this 4x here and this 4x here. So we're going to be able to actually solve this with factoring. So let's come down a little bit and let's plug in. So this goes in here. So negative 2, and then sine of, you have your 4x, and then sine of, you have your 2x, and then plus your sine of 4x, and this equals 0. So you have your sine of 4x and your sine of 4x. So we are going to factor that out. So let's factor that out. So out in front of some parentheses, you would have the sine of 4x, and then inside, you would have negative 2 sine of 2x. So negative 2 sine of 2x, and then plus, if this gets pulled out, you're going to have a 1, and then this equals 0. Now at this point, you can use your zero products property. So you can say that the sine of 4x is equal to 0, or we're going to do this one. So negative 2 sine of 2x plus 1 equals 0. In this particular case, you have sine of something. It doesn't matter what it is. In this case, it's 4x equals 0 or some number. This is okay. For this, when you want to clean it up, you would want sine of 2x equals some number. So let's go ahead and subtract 1 away from each side. This cancels. So actually, let me just erase it so we can save some space here. And then I would divide both sides by negative 2. So this would cancel. So you're going to get the sine of 2x is equal to 1/2. So positive 1/2. Now, here's where you need to make a decision. Again, in most cases, you're going to solve for the general solution. And when I solve for the general solution, I like to use a substitution technique. So you can do it this way if you want. If you're solving over an interval, you can do it the normal way that we've been doing it by adjusting our interval. So instead of sine of 4x equals 0, for this particular one, I'm going to let u be equal to 4x. Now this has nothing to do with this. So actually, let me cut this away and put this on another page so nobody's lost, because people will get confused. So now I can solve this, let me get rid of this or, by saying that I have the sine of u is equal to 0. So if I look at the sine of u equals 0, using my unit circle, let me write this in. So the sine of u equals 0. So if you look at this guy is 0, so that's at 0, and then this guy is 0, that's at pi. So you could write that u, in terms of the general solution, is equal to 0 plus 2 pi n, and then you could say pi plus 2 pi n, where n is any integer, because things are going to repeat every 2 pi in terms of u. Now, what you could actually do is write this as 2 pi n, and then pi plus 2 pi n, but you would notice that actually you can combine those solutions and make it a little bit more concise, because things are happening every pi. So in other words, I could just write this as pi n. So I could write this as pi n, because if I plugged in a 0 for n, I'd have 0. If I plugged in a 1, I'd have pi. If I plugged in a 2, I'd have 2 pi. At 3, I'd have 3 pi, so on and so forth. So this is the general solution in terms of u. So let's come back up, and let's say that u is equal to pi n. Now, we let u be equal to 4x. So all I have to do is plug in a 4x for u. So 4x is equal to pi n, and then just solve for x. How do I do that? I divide both sides by 4. So this would cancel, and you're going to get that x is equal to pi over 4 times n. So let me get rid of this and bring this over here. So x is equal to pi over 4 times n. Now, we will get our solution in the interval in a moment. Let me get rid of this, and let me come down here and solve this. So I'm going to use u again, but it's only in terms of this. It has nothing to do with what we did before. And actually, so nobody gets lost, let me just pick something else. Let me let w, so nobody is confused, be equal to 2x. So now I want to solve the sine of w is equal to 1/2. Come back to the unit circle, and let's think about this. Again, sine of w equals 1/2. Well, we know how to solve that. We know that solutions are going to repeat every 2 pi. So where's the y-coordinate 1/2? So right here at pi over 6, and then that's going to be right here at 5 pi over 6. So we can say that w is equal to pi over 6 plus, again, these solutions repeat every 2 pi. Again, this is in terms of w. So we're going to say 2 pi n, and then we're going to have 5 pi over 6 plus 2 pi n. Again, things are happening every 2 pi in terms of w. Okay, so in terms of w. So let's grab this. All right, so let's come back here. Let's get rid of this. And now w is 2x. So all you have to do is go back and say, okay, well, 2x is equal to, we have pi over 6, and then plus you have 2 pi n. The other one is 2x is equal to 5 pi over 6 plus 2 pi n. Let me get rid of this. And actually, I probably should slide these over a little bit because I have to do some multiplication here. Let me make that border a little bit better. And let me slide this down just a little bit and slide this up just a little bit. Now, we have 2x, not x. So if you want x by itself, you can divide everything by 2, But because we have a fraction involved, it's better to multiply by a half. It's just a little bit easier to do it that way. Let me get rid of this border here. So multiply by a half and then multiply by a half. So we know that this would cancel and just give me x is equal to pi over 6 times a half is pi over 12. And then plus 1/2 times 2 pi n. The 2's would cancel. You just have pi n. So get rid of this. So that's one guy there. Let me move this over. And then this guy, I'm going to do the same thing. So let me move this up. I'm going to multiply this by 1/2, multiply this by 1/2, and multiply this by 1/2. So we're going to see that the 2's are going to cancel. You're going to have x is equal to, if you have 5 pi over 6 times a half, well, we would have 5 pi over 12. And then plus, again, the 2's would cancel. So you're going to get pi n. So let me get rid of this. And actually, this color really doesn't show up very well. So let me change this and say that x is equal to pi over 12 plus pi n. And then we have 5 pi over 12 plus pi n. Okay, let me bring this back here. And now let's put our solution together. So right now I'm giving you the general solution, and then I'll give you the solution over an interval. So for the general solution, you're going to take this one. So we're going to say that we have pi over 4 times n. Then if we think about this one, we have pi over 12 plus pi n. And then this one is 5 pi over 12 plus pi n. That's our general solution. Now, if we want to go with the solution where x is greater than or equal to 0 and less than pi, well, again, you're going to start here and plug in a 0 for n. So that would give you, let's go x is equal to 0. And if I plugged in a 1, I'd have pi over 4. If I plugged in a 2, I'd have 2 pi over 4, which is pi over 2. If I plugged in a 3, I'd have 3 pi over 4. If I plugged in a 4, I'd have 4 pi over 4, which is pi, and that's not in this interval, so I'm going to stop there. And then these, you would have pi over 12 if you plugged in a 0 there. And then if you add pi, you're not going to be in this interval. So then this one, I would have 5 pi over 12, so 5 pi over 12. Again, if I add pi, I'm not going to be in this interval. So these are your solutions in this interval. So 0, pi over 4, pi over 2, 3 pi over 4, pi over 12, and then 5 pi over 12. Okay, so I want to think about this graphically with you. If you're struggling with finding the general solution, this can be extremely helpful, although it's extremely time-consuming to think about this with a graph. So we have y equals the cosine of 6x minus the cosine of 2x plus the sine of 4x. So this was my equation. It's just that instead of y, we had 0 over here. So if I plugged in a 0 for y, so in other words, if I had 0 is equal to the cosine of 6x minus the cosine of 2x plus the sine of 4x, all I'm doing is I'm saying, for which x values am I going to get a y value of 0? Well, where is y 0 when I'm thinking about this on the coordinate plane? Well, that's on the x-axis, right? So that's where y is 0. So anywhere where I cross the x-axis or have an x-intercept, I'm going to have a solution for this equation. So thinking about this, where x is greater than or equal to 0 and less than pi, I get this graph right here. Now, in a moment, we're going to talk about the fact that the period for this guy is going to be pi. We discussed this in the last practice test. Maybe you didn't watch the video for that, but I'll explain where this is coming from in a moment. So that means that I can go from 0 to pi, and I'm going to include 0 and exclude pi, and any solutions I find will actually repeat in that next cycle. So I could just take that solution and add pi. But you're going to see that you can condense some of those solutions that make it a little bit simpler. And let's just start with what we have. So notice that you have this 0 here, so that matches this one. I'm going to skip this one over for a moment. So we have this pi over 4, so that's there. I'm going to skip this one, so this is pi over 2, so that's there. And then I'm going to go to this one, which is 3 pi over 4. Now, if you think about those solutions, you have 0, and then you have pi over 4, and then you have pi over 2, and then you have 3 pi over 4. Again, you could go through and say plus pi n, and then plus pi n, and then plus pi n, and then plus pi n. That is valid. But what's happening is, if you add pi to this, let me just show if I added pi, this would get me to pi. If I added pi to this, I would be adding 4 pi over 4, so this would get me to 5 pi over 4. If I added pi to this, that would get me plus 2 pi over 2, so that would be 3 pi over 2. And then if I added pi to this, I would add 4 pi over 4, so that would get me to 7 pi over 4. Well, if you go through here and you just look at these first guys here, so it would be a jump of pi over 4 each time. So 0 plus pi over 4 is pi over 4. Pi over 4 plus pi over 4 is pi over 2. Pi over 2 plus pi over 4 is 3 pi over 4. 3 pi over 4 plus pi over 4 is pi. Pi plus pi over 4 is 5 pi over 4. 5 pi over 4 plus pi over 4 is 3 pi over 2. 3 pi over 2 plus pi over 4 is 7 pi over 4, and so on and so forth. So that's why we got that pi over 4 times n with the general solution. So we have this pi over 4 times n. Then the other ones, you really can't do anything with them other than to say that you have pi over 12. So that's this one right here, and then just plus pi n. So it's just going to repeat in the next cycle. So this is pi over 12 plus pi n. Let me slide this down. And then the other one, we have 5 pi over 12. So that's this here. So again, that's just going to repeat in the next cycle. So 5 pi over 12 plus pi n. All right, let's come to the graph. Now, these solutions are extremely hard to read, so you probably need to follow me on Desmos or something like that in order to fully see everything. But I'm just going to first talk about the period for this guy. I'm going to let you visually see that and explain where it's coming from. So in the practice tests for the last lesson, we talked about the fact that if you had something like y equals the cosine of 6x minus the cosine of 2x plus the sine of 4x, if you wanted the period for this, then basically you would think about the least common multiple of the periods. So how do you get the least common multiple of the periods? So this right here, you'd think about it as, let's just say you had y equals the cosine of 6x. What's the period? Well, it's going to be 2 pi over 6, right? 2 pi over 6, which is pi over 3. So pi over 3. Again, that's coming from that formula. If you have y is equal to the cosine of bx, well, it's 2 pi, which is the standard period for cosine, divided by b. So here it's 2 pi divided by 6, so that gives me pi over 3. It's the same thing if you run into sine, right? So sine and cosine is the same thing. So let's do this one. So this is the cosine of 2x. So that's 2 pi over 2. So that gives me just pi. And then for this one, it's the sine of 4x. So that's 2 pi over 4. So that's pi over 2. So we have not discussed how to find the least common multiple of fractions. So in other words, let's say I said, what is the least common multiple of 1/3, 1, and 1/2? Well, some of you know that it's going to be 1, but others don't. Now, there's a formula you can use for it, but it's a little bit complicated, actually, if you ask me. I think it's a little bit faster to just list things. So if you had something like pi over 3, all you're doing is you're multiplying it by 1, then 2, then 3, then 4. You're generating some multiples. So times 1, it would just be pi over 3. And then times 2, it would be 2 pi over 3. And then times 3, it would be 3 pi over 3, which of course is just pi. And then we could just do one more. So times 4, it would be 4 pi over 3. Let me put a border. For this one, if it's pi, well, that's real easy. Multiply by 1, you get pi, then 2 pi, then 3 pi. Let's stop at 4 pi. Then for the other one, you have pi over 2. So let's go times 1, it's pi over 2. Times 2, it's 2 pi over 2, which of course is going to just be pi. And then times 3, it's 3 pi over 2. Times 4, it's going to be 2 pi. And you could stop there. If you look at the least common multiple here, well, looking through, what do I have that's common to everything? You have pi, you have pi, and you have pi. So in other words, if you had 1/3, if you had 1, and you had 1/2, the LCM would be 1. But in this case, we have pi over 3, which can be thought of as 1/3 times pi. You have pi, which can be thought of as 1 pi. And then pi over 2, which you could think of as 1/2 times pi. So the least common multiple there is pi. So that tells me that the period for this graph here is going to be pi. Let me get rid of this. And let me actually trace this out so you can see it. If you want to follow me, type in x is equal to pi like this in Desmos. It's going to fix it for you and give you a pi like that. You're going to get a vertical line. And you can go x equals 2 pi, and then x equals 3 pi, so on and so forth. You're going to get these vertical lines, and it's going to really allow you to see the period of this guy. So I'm just going to trace from 0 to pi, and then we'll see that this is going to repeat from pi to 2 pi. So this right here, this is going to be one cycle for this graph. So this is one cycle. So from 0 to pi. And then again, if I went from pi to 2 pi, the same thing is going to repeat. So basically, I come up, come down, come back up, come down, come back up. So this is way up here. This is exactly matching what happened in the last cycle. So you can see that these two match and the period is going to be pi. So this tells me that things that happen from 0 to pi, 0 included, pi excluded, would happen again from pi to 2 pi, pi included, 2 pi excluded. So that's how we ended up on the last page where I did this where you could see the solutions more clearly. And it looks like I erased my 5 pi over 12. But as I was saying, it just shows you that solutions that happen in this cycle will repeat in the next cycle. So you could take your 0 plus pi n. You could take your pi over 12 plus pi n. You could take your pi over 4 plus pi n, so on and so forth. It's just that the 0, pi over 4, pi over 2, 3 pi over 4, those guys can be condensed into this form right here. So the pi over 4 times n, where n is any integer. And then for your pi over 12, well, you really can't do any better than just saying plus pi n. So you have your pi over 12, you add pi, that gets you to that 13 pi over 12. I know you can't see it, but it's right there. And then 5 pi over 12, again, if you add pi, you're going to be at that 17 pi over 12. Again, I know it's hard to see, but just follow it on Desmos if you want to look at it. So this is our general solution. Again, if you want to play around with the graph on Desmos, you can visually see this, and it'll help you to understand the concept of the general solution and how things are repeating.